Geez, I have students missing right now. Today, thought I better wake you up since we got an evening class here. So here's one of my more favorite math questions. What is this product? X minus A, X minus B, X minus C, all the way down to X minus Z. All right. What does that come out to? This shows how learning too much sometimes makes you stupider. You guys all know this before you took all this advanced math. Anybody know this one still? Still have a brain? It's really easy. Everybody tries to analyze it and figure out the binomial formula, this kind of thing. In fact, it's zero. Why is that? Anybody online know? Because somewhere in here, there's an x minus x factor, right? And x minus x is zero, multiplies the whole thing is zero. Hold on. Reminds me of another one of my friends who taught here years and years, and sometimes he still adjuncts teaches, told me that he knew somebody who didn't like OU football, and so he bet his friend who did like OU football that the sum of the other team's scores would be bigger than the product of all of OU's scores for the season. And his friend thinking, boy, I'm going to win this. OU's product score is going to be big. Was willing to bet him, but at least in those days, every once in a while, OU would get shut out. And what happens is once they get shut out once, the product of all their scores is zero. And they got mad at his bet, I think. Anyway, so there's some fun just to start off. Maybe wake you up. Well, tonight, I hope that you'll interject questions. Let me turn up the volume here. In fact, not too bad. This lecture hopefully will remind you of what you saw in Calculus 1. And I think if you just relate it to what you've seen before, it'll be straightforward. And I hope being awake and having this be straightforward, we'll learn something. All right. So maxima and minima, you've seen that before in Calculus 1, but this time we're going to do it for functions of two variables. This is multivariate calculus this semester, right? So in order to understand what's going on there, let's review first Calculus 1. A function of one variable. Y equals f of x. What did we say about finding local relative? A review, excuse me. What did we learn about functions of one variable? Well, let's see. Suppose we're looking at relative extrema, relative max or min. Well, what is it? A function has a relative extremum at x0 if on some open interval, no matter how small, containing x0, say from here to here, f of x0 was bigger than or equal to f of x. So if on some open interval containing x0, so that x0 is an interior point, you can do a closed interval as long as x0 is an interior point, but it tends to be defined this way. Suppose we have this kind of thing where f of x0 is the highest point on some open interval. We only take the points from here over to here, and we call it a relative extrema, right? This would be a relative extreme point. It might be that it goes off over here and is bigger, but this is still a relative maximum. Similarly, this y is a relative minimum. F of x1 at x1 is a relative minimum. If on some open interval including x1, it's the lowest point. So relative maximum of the y coordinate, f of x0, at x0 occurs if f of x0 is bigger than or equal to f of x on an open interval containing x0. That was what we did before. And then here, relative minimum of the y coordinate, the dependent variable, f of x1 at x1, if f of x1 is bigger than or equal to, is less than or equal to, excuse me, f of x on an open interval containing x1. So this makes rigorous our view over here. But if we want to call this a relatively minimum point, it may not be the lowest lowest point overall. Look, the function shoots off like that. This may not be the highest maximum overall, but if on some interval, it's like Horton, here's a who, remember? Person's a person, no matter how small. Anybody read that when they're a kid, right? Well, maximum is relative maximum is a relative maximum, no matter how small the interval. You just have to have it be the maximum on some interval, no matter how small. That was the concept, right? Now, how do we find those? How do we determine a relative maximum?
Normally, you just look at a graph, right? Or if it's given.
Yeah, there's a good theorem. Yeah, every relative extremum, relative max or min, occurs at a critical point. Of a function, which is a point where what? A point where the derivative is 0. Critical point meaning just the x coordinate. Critical point of the x-axis. Point x0 where either the derivative is 0 or does not exist. So that really narrowed down where we had to look. We know everyone occurs at a relative extremum, or at a point where the derivative is 0 or doesn't exist. And that's what we're looking at over here, right? In these two cases, we've got a horizontal tangent line, so the derivative doesn't exist. Excuse me, the derivative is 0. And in general, if you draw another function, it might have some points like that where it's got a relative min or max, and the derivative is 0, or it might have points like a corner here, x1, where there's a relative maximum, and the derivative doesn't exist because, right, the derivative from the left is one value, the derivative from the right is the other. Derivative doesn't exist at this point. Or it might be something like this. Here's a relative minimum at this point, right? X2. But every relative min and max occurs at a critical point. Here's a point where the derivative doesn't exist because it's discontinuous, right? However, we have this unfortunate situation. We can have it go up to a point like this and jump down here. So this one has a relative max of that y value at this x value. This one has a relative min of this y value at this x value, but not every critical point produces a relative max or min. For instance, this one right here, x3, let me put this one, I guess I should have put this one at x2 there's a relative minimum here, because on some open interval, right, you're taking this piece of this part, and the lowest y value is right here in the middle. However, on this one is neither a relative max or min, right? Why is it not a max or min right here at this y value? Because it doesn't take on that value, right? It gets closer and closer. When it's a least upper bound, we can call it a supremum. So we can say this is a supremum of the function, but it's not a maximum. A maximum is a value the function actually takes on, right? It's a value f of x0 that's greater or equal to all the other points, but there is no f of x0 at this point, right? It's down here. It's not the maximum. It's down here, excuse me. And so if you've got this kind of you can have these kind of points where it's a critical point because the derivative doesn't exist at the discontinuity, but it's neither a relative max or min. You can also have this kind of a case where it comes down and straightens out. If you do this just right, this is still a function, but it's got a vertical tangent here, and this one is also neither, right? It goes up on this side, down on this side. It's not a relative max or min, so this one's also neither. So every relative extremum occurs at a critical point, but not every critical point x0 produces a relative extremum, max or min, the y coordinate, f of x0. That's what we did. And so we say that a critical point, looking at a critical point is a necessary condition for an extremum, right? Critical point's a necessary condition, but it's not sufficient, right? It doesn't guarantee that there is an extremum there. It just narrows down your choice. So how do we find a sufficient condition to know that there's an extremum there? Well, we had a theorem, right? That said, if there were two theorems, I should put both of them here. Well, there's a first derivative test and there's a second derivative test. And the first derivative test went like this. I'm just going to draw it because we're not going to need it tonight. So you can have a point x0 here, and it said that if the first derivative was positive on this side and negative on this side, then this was a relative maximum at this point. So if on an interval, on an open interval, one of them going to the left of x0 and one going to the right of x0 of a continuous function, have this case plus on the left and minus on the right if you took the slope of the tangent lines. Then that was a relative maximum. The other one was if you had a continuous function like this, where the derivative was negative on the left, right, slope of the tangent line down, and the derivative slope of the tangent line was positive on the right, then that was a relative minimum. So a continuous function, derivative one sign on an interval to the left, another sign on an interval to the right. So let's say this interval and this interval. You could determine whether it was a relative max or min that way. Another way was the second derivative test. If you had a function like this that had a second derivative at a point, say x0, and it's a critical point, and it said that if f double prime, the second derivative at x0, was positive like this, right? It's concave up. Remember, the second derivative makes it concave up. You don't actually need concave up in the interval, all you need is second derivative positive at the point. But I like to think of concave up, because if it's positive in an interval, it'll be concave up. If the second derivative is positive at a point, what did that tell you at a critical point? That told you had a relative minimum, because second derivative positive, think of concave up. If it's on an interval, it'll be a concave up. And so it has to be a minimum when the second derivative is positive. That was kind of counterintuitive. You think positive must be a max, right? No, positive second derivative at a critical point made it a minimum. Then we could have this kind of case where we had a point x naught that was a critical point. And these only apply to critical points where the first derivative is zero, because if the first derivative doesn't exist, then the second derivative doesn't exist. You can't apply this test. So for critical points where the first derivative is zero, sometimes we call those stationary points where the derivative is zero. At a stationary point, if the second derivative is negative, think of concave down, because if the second derivative exists on an interval, it'll be concave down. Then that gave you a relative maximum. So second derivative less than zero at the point tells you it's a relative, where it's continuous, tells you it's a relative maximum. Second derivative positive at a critical point where it's continuous tells you it's a where it's a stationary point, tells you it's a relative minimum. So these were both sufficient conditions. So what you did in calculus 1 was you first went through and found all the critical points. So because you can't check an infinite number of points, right? But you'd find the critical points and then you'd have it narrowed down. Then for each one, you'd apply either the first derivative test by checking the derivative on each side of the critical point, x0, or the second derivative by plugging in the second derivative just at the critical point was all you had to do, right? And that found relative minima and maxima. All right. So now we want to extend this to calculus 4. Say similarly, let's seek relative extrema of a function of two variables, z equals f of xy, in a completely analogous way. First, we need a definition, right? I didn't read about it. Here's the definition. If on some open disk instead of an open interval at a point x0, y0, f of x0, y0 is bigger than or equal to f of xy. Then what should we conclude? The picture is immensely helpful here. We're now doing in 3 dimensions. We have some point in the xy plane down here. x0, y0 in the xy plane. You put a 0 in here if you include the z coordinate. But I'm really just interested in the xy plane. And I take some disk at there, and then I have a surface up here, z equals f of xy. And suppose this function f of xy is defined in a disk containing that point. And now if you go up to the point here, there's an image of the disk over this, and I maybe should draw it dotted since it's an open disk. It can be closed or open. It actually doesn't matter, but they usually define it open. Here's the image up here on the surface. If the very highest point, the z coordinate here, is the highest, bigger than or equal to all the other z coordinates on this region over the disk, then we say it's a relative maximum. Another word for it is local. In some textbooks, instead of saying relative maximum, they'll say local maximum. So relative or local maximum. That's the definition. You have to find some disk, no matter how small, just like in calculus one, for a function one variable, you found an interval about the point, no matter how small, right? On which you had a highest point by the function was bigger than equal, at that point was bigger than equal to the function of all the other points. Similarly here, on an open disk, no matter how small. If f of x0, y0 is the highest point, we say it's a local maximum, right? And b, similarly, in calculus one, if you found a little interval of the function of x, no matter how small, such that f of x0 was the smallest value, it was the relative minimum. Similarly here, we'll look at an open disk in the domain of the function. And if f of x0, y0 is less than or equal to f of x on the disk, then we call f of x0, y0 a relative or local min. All right, so a nice analogous definition, right? Now, how shall we similarly find relative extrema? How do I say for this surface, find that this is the relative maximum? I know I'll first narrow it down by finding the critical points. And then once I have the critical points, I'll do something similar to the first or second derivative test and to determine which one actually are relative min or max, because just like functions of one variable, critical point is not a sufficient reason to say it has a max or min. We'll just know that every max or min occurs there, and then we'll have to find some secondary test to decide which ones are relative minimum, maximum, and which ones aren't. For that, we need actually to introduce another definition here first. Well, let's see. Now let's do this. Now, similarly here, in order to narrow down the places we're going to look, we're going to say a critical point of a function of two variables is a point in its domain. Now, two variable point, x0, y0, at which both partial derivatives are equal to 0. df dx and df dy are both 0. It will be a critical point. We'll call that a stationary point. But just like in calculus one, you can have a point where the derivative doesn't exist. If either partial derivative doesn't exist, then it's also a critical point. Either or both. So just like calculus one, you point it where you want to point at which the derivative of 0 doesn't exist. Now you want to point at which both partial derivatives of 0 or at least one doesn't exist. And then this wonderful theorem, an analogy to calculus one, I think this is attributed to Fermat, every local extremum, max or min, of a function of two variables f of x, y occurs at a critical point. So there's a necessary condition for a critical point for a function, for a relative max or min of a function of two variables is also has to be at a critical point. That'll narrow it down a lot for us. I should tell you another story here since we're far enough along here. And like I said, I'm pretty sure this theorem is due to Fermat, or at least named after him. Ever heard of Fermat's last theorem?
Yes. No.
Did you have a question? Is it?
Oh, no.
Oh,
Yes.
all right. There's this wonderful theorem attributed to him. His most famous theorem is this one. You've seen where x squared plus, or a squared plus b squared equals c squared can be whole numbers. This is an aside from what we're doing. Right, like a 3, 4, 5 right triangle, 3 squared plus 4 squared equals 5 squared. We call those Pythagorean triples because then you make a triangle with those. Or 5, 12, 13. 5 squared plus 12 squared is 13 squared. And so there are whole number solutions. We call those Pythagorean triples. And mathematicians began to wonder, of course, well, maybe there's some solution if I put cubes here. And I do this in higher dimensions or something, or make more exotic figures. And you know what? They could prove that there were no whole number solutions when you put, well, maybe we just need even powered, right? A to the fourth plus b to the fourth equals c to the fourth. No whole number solutions. They went higher and higher, and they went huge numbers. A to the n plus b to the n equals c to the n. No matter how high a power they took, they could not find whole number solutions. Look up Pythagorean triples on Wikipedia. It's a very fun article. They show you there's an infinite number of solutions with squares here. Actually, I mean, their positions of the plane look really neat, or in the AB plane. Anyway, mathematicians began to wonder if maybe there is no number n, no matter how big, for which you have whole number solutions, that it ends at 2. But alas, nobody can prove it. It's a very, very difficult proof, believe it or not, extremely difficult. But Fermat was such a brilliant mathematician, he found a proof, he said, and the margin of the page was too small to include it. But he said it was a real marvelous proof. Then he died, and nobody knew what the proof was. And for hundreds of years, of course, nobody could figure out what his proof might have been, and nobody could prove it. It was so hard. Finally, in the 1990s, a guy named Andrew Wiles, I think he was out at Princeton last I heard. Maybe he's retired by now. I don't know. Came up with this proof with number theory so advanced that hardly anybody in the whole world can understand it. It depended on these really difficult theorems. How could such a simple result that a to the n plus b to the n equals c to the n has no whole number solutions for n greater than 2? But they say he proved it. I can't understand the proof myself. I don't know all that. But supposedly it is true, but it bears Fermat's name because it's such a famous result that was so hard to prove for hundreds of years. And even now, there's so few people that can check the proof because it's so hard. It's surprising. And sometimes you get these proofs and they're unprovable because there's just not enough axiom in mathematics to decide whether it's true or false. But this one actually is true. And even though people worked on it a long time. But anyway, there's another one due to Fermat. That's really famous. I would wake you up with that. All right, so every local extremum occurs at a critical point. Now, on top of that, we need another test to determine a sufficient condition to know that we have a critical point. What should we do to check each critical point to see if a relative max or min occurs there?
Taking derivative.
Well, it turns out that the analogy to the first derivative test, we're going to look at the derivatives. If we look at the first derivative, it's kind of hard because there's so many different cases, right? You can don't draw this, but can you imagine it can come up to a corner like that with flat sides here, and then you have to consider the flat sides, or it might be rounded on one side and flat on the other. And there's all these different cases to consider where it kind of comes up to a top value, and you can prove something that way, but there's so many cases that we don't make a theorem out of it. You just kind of do it on an ad hoc basis. So we aren't going to do any analogy to the first derivative test. We'll just say, do it as you find your own method for the kind of function it is. Instead, we're gonna do this theorem, which is an analogy to the second derivative test. And it says this, so we call it second partial test, in fact, in your book. Because of its analogy. If we want to prove that a critical point for a function of two variables is a relative max or min, we can use this. If f of xy has a continuous second partial derivative, fxx, fyy, fxy, fyx at a point. And this stuff is, like I told you, calculus is incredibly detailed. You have to really think about this. There's all sorts of assumptions entailed in this. For instance, this isn't along the boundary of a domain of a function, right? It's only an interior point. Can you see why? Like if I have a function here, it's defined like this on a square, it can't have a relative extremum on the edge of the square. Why not? Because when we say a relative extremum, it means there has to be a disk about it, which is the highest point. But if you're on the boundary of the domain, if this is the domain and this is the surface, if you're on the boundary, there is no disk on which it's defined, no matter how small you're on the boundary. What it means to be on the boundary is that there's points, if you make a disk about it, there's points inside and outside the region of definition. So this entails that this is an interior point. Things like that. And these second partial derivatives exist, of course, if and only if not if and only, requires that the first partial derivatives exist. So you have to have slopes of tangent lines everywhere within the region, right? So it's that kind of thing. Now, with all those assumptions, suppose these second partial derivatives exist, then we're going to do this. We're going to define D, and this is our short notation for second derivative, right? D is going to be equal to fxx, fyy minus fxy squared. And this will be at the point. I don't want to write of x0, y0, of x, y0, x of x0, y0. So let D be equal to that at the point. This one you just have to memorize. Suppose that's the case. Then we're going to say this: A, if D is positive, and better move this over a bit, sorry. Going off the screen a little. If D is positive and partial of f with respect to x at the point, second partial, is positive, what do you think is going to happen? This is where intuition helps you to remember this theorem more than just memorizing line for line like it's your Greek class or something, French class. If D is positive and fxx is positive, then this is what happens. At the point x0, y0, second derivative positive, think of concave up like we did with the functions of one variable. But this time, suppose it's concave up in all directions, even though I just said it's concave up in the x direction is what this proves, right? If you're moving in the x direction, this direction, that says you have a concave up thing at the point. I should draw it so it looks like a minimum. So here's a point that I think maybe is going to be minimum because that's a critical point where both partial derivatives are equal to 0. Here's the intuition. Fx equals Fy equals 0. So when we apply this test, it automatically assumes that the first parcels exist because otherwise you can't have second parcels. It means that what you have is this, a horizontal tangent plane, both partial derivatives are equal to zero. And continuous. It's not the case where you have the partial derivative doesn't exist. You can't apply this test where the partial derivative doesn't exist. But you have a horizontal tangent plane. Then you want to know if you move in the x direction and you take the slice of this plane in the x direction and find the slope of the tangent line. Suppose the second derivative is positive so that the trace is concave up. Oh, it must be that this is a relative minimum. F of x0, y0 is a relative minimum of the function. So it has to be in an interior point of the domain where you have a horizontal tangent plane. And now if the second parcel with respect to x at x0, y0 is positive, then it's a relative min. Again, it's backwards like in calculus 1. Positive second derivative means minimum. Negative second derivative is going to be a maximum. Similarly, if t is greater than 0 and f x at the critical point, and I forgot to put a very important part here. Continuous at x0, y0, a critical point. Only applies to critical points. Let t be defined this way, critical point. Now, if t is greater than 0 and fxx at x0, y0 is less than 0, just like in calculus 1 is backwards, second derivative negative, backwards thinking, means it's actually maximum. Then f at x0, y0 is a relative or local maximum. So second derivative negative is a max, second derivative positive is a min, just like in calculus 1. With the same reasoning, similarly, got some surface with a horizontal tangent plane, fx equals fy equals 0 at the point. Then I take, oops, I drew it the wrong way, didn't I? Oops, try again. Supposed to be a maximum this time. Go. So maximum up here with a horizontal tangent plane. And now you take the trace moving in the x direction, and it's concave down because the second partial derivative in the x direction is negative. Then you say, oh, it must be a maximum. And sure enough, it's true. But then you say, wait a minute. Just because it's concave down in this direction or concave up in this direction doesn't prove it. What's going on? Well, the d comes in here. If d is positive, it means all the second parcels in all directions have the same sign. When this quantity is positive, then it doesn't matter if you go in the x direction, it'll be, or the y direction, it'll be the same concavity. Concave up in the x direction and d positive mean it'll be concave up in the y direction, or any directional derivative, it'll be concave up. Similarly, here it'll be concave down in all directions. If d is positive and it's concave down in one direction. So that's the purpose of d. And here's the third part of it. You have something that's not in calculus 1 because you don't have enough dimensions. But if d is less than 0, then x0, y0 is a saddle point. What's a saddle point? It's the other case. Some of the second parcels are positive at the point, some of them are negative, depending which direction they're moving, so it switches. So it's neither a relative min or a relative max. In that case, has a picture like this. You've already seen it with the hyperbolic paraboloid. If you took it in my class, then you already learned it. Right, that's the hardest of the quadratic surfaces, but it's easy for Oklahomans because it looks like a saddle, right? So that was this kind of a case where you'd have here's a hyperbolic paraboloid, something like that. And at this point right here, there's actually a horizontal tangent plane, right? Right at the center of the seat of a saddle, but it's concave down in this direction and concave up in this direction. And so it's neither a relative min or max, right? If you move in the x direction, in this one, the second derivative is negative because it's concave down. Moving in the y direction, the second derivative is positive, it's concave up. So there's a saddle point that's neither a relative min or max. So there's the equivalent, or the analogy, I guess I should say, to the second derivative test of calculus 1. And we apply it in the same way. We first find all the critical points. And then once we have all the critical points, we test each at the point only. We don't have to test around it like in the first derivative test. The second derivative is positive with d positive, then it's a relative min. If the second derivative is negative with d positive, then it's a relative max. But if d is negative, then it's a saddle point. Okay? And that's all there is to it. It's very similar. I hope you can see that, and then this homework will all be better. Same kind of concept. These are long problems in this section, actually. So I haven't assigned a whole lot of them, but don't take that to mean you should put off doing the homework. Here's an example. Suppose f of xy is equal to x cubed plus y cubed minus 12xy, defined everywhere on the plane, right? Find the relative extrema and saddle points. How do I find that? It's like calculus 1, right? 1, find the critical points. 2, apply the second derivative test to each. I mean, there is no analogy to the first derivative test. You just do it on a case-by-case basis, right? So the critical points, what do? In calculus 1, we set the derivative to 0. There's only one derivative. In calculus 4, we set both partial derivatives equal to 0. So we'll say 0 equals partial of f with respect to x is, let's see, 3x squared minus 12y. And we set the first partial with y respect to 0. First partial with respect to y equals 0, which is 3y squared minus 12x, right? And we need both of these to hold in order for it to be a critical point, or that one of them doesn't exist. But look, this is a polynomial in two variables. The partial derivatives exist everywhere, so this is all of them, right? For polynomials, the derivative exists everywhere. There's no points where we have to worry about the other cases. Well, this is good for us because that means we can apply the second derivative test to any of these that we get. How shall we determine what the critical points are? You have to, by hook or by crook, come up with these. First thing you might do is reduce them a little and say, oh, I'll just divide that by 3 and get x squared minus 4y equals 0. And divide this by 3 and get y squared minus 4x equals 0. And then you have to solve these equations in multiple variables. Find how you can make both of those equal to 0. Fortunately, these are just in the xy plane. So what is this one? This one is y equals 1/4 x squared. So this one is the parabola that looks like this. That's y equals 1/4 x squared. I need to be lying on this parabola in order for the first partial of f, the function of two variables, which is the surface and free space, to have its partial with respect to x equal to 0. Now, what is this one? If you look at this one, this is y squared x equals 1/4 y squared. This is a parabola opening about this other axis. And so it looks like this. All right, we know that looks like that. Here's x equals 1/4 y squared. And now we have a pretty good idea. We noticed immediately they intersect at the origin. Oh yeah, but x and y both 0. That's an obvious solution. So 0, 0 is a critical point. But we observe since these are two parabolas, they're going to intersect out here somewhere too. So we can find the other intersection points by solving these two equations simultaneously. Let's put these things together and say, well, if y is 1/4 x squared, but x squared is this squared, it's 1/16 y to the 4th. X is this, then x squared is this. Here 1/4 that equals 1/4, and replace x squared with this one, 1/16 y to the 4th. I then have that y equals 1/64 y to the 4th. Now, you have to be careful because the thing to do here is to divide through by y, but that throws out the solution y equals 0. So we already checked the solution where y is equal to 0. That's just the origin. So now we can divide through by y without losing any solutions. We'll say 1 equals 1/64 y cubed. All right. Tells me that y has to be the cube root of 64. Oh, we know what that is. That's just 4, right? 4 times 4 times 4 is 64. So it has to be at y equals 4, and then by symmetry you deduce that x equals 4, or plug it into either one of these. 1/4 of 4 squared, 1/4 of 4 squared is 4 for x also. So I get the point here, 4, 4. But you solve these by hook or by crook, and I'll tell you something, and for complicated equations, this can be extremely difficult because what you're doing is solving two nonlinear equations, and there is no nice, just like there's no nice way to do the first derivative test for all surfaces, there's no nice way to deal with all nonlinear equations. Linear equations are easy. You ever take linear algebra, anybody? It's a nice, clean subject. If you get a system of linear equations, it's easy, but nonlinear equations like this, where you have squares and so forth, there is no tried and true technique. The usual way you do it is you solve for one variable in one equation and substitute in the other, and that's what we've done here. Right, y equals 1/4 x squared, but x is 1/4 y squared, so we're substitute for x in here and get y equals 1/4 instead of x squared, put 1/16 y to the 4th. That's the main technique people use to solve these nonlinear equations. Solve for a variable in one equation, substitute in the other. But beyond that, it's lots of different things. Sometimes you add a multiple of one equation to another and eliminate a variable. Lots of things can happen. Well, I'll just say that you just have to use your own intuition sometimes on those. The book won't make them too hard for you. You know, you can look at them and do something like I did here with the picture that sometimes helps. So there's the two critical points. 0, 0, and 4, 4 are the only critical points. The only places where the parabolas intersect. So now what do we do? The second step is to apply the second derivative test to each. Since we have something that derivatives of all orders exist, we'll apply the second derivative test. Apply the second partial test, I should call it, to each. For that, we need the second partial, right? So we have the first partials here. Let's just use them, right? Partial with respect to x was 3x squared minus 12y. So fxx is the partial that we already computed, taken with respect to x, is the partial of 3x squared minus 12y with respect to x is, oh, it's just the partial with respect to y is 0, so this is just 6x, right? And second partial with respect to y, well, we take fy that we computed, and take partial with respect to y again. Fy was 3y squared minus 12x. We'll take partial of that with respect to y is 6y minus 0. So that's 6y. Now finally, we need the second, the mixed partial, fxy. And so we can do either order, it doesn't matter. We'll take partial with respect to x and then partial with respect to y. Again, what we said before was except in pathological cases, that fxy and fyx taken in either order are equal. So because this is demanding continuity at the point, continuity of the second partials at the point, these two will be equal. All right, so fx was 3x squared minus 12y. We're going to take the partial of that with respect to y, which comes out to be minus 12. There we go. So there, now to apply the second partial test, we need to compute d. Right? D is again fxx fyy minus fxy squared at the point. I didn't draw it over there, but I said it at the point where the point is. Well, let's say. Oh, all right, at the point x0, y0, let's say. All right, so now we can compute all this stuff. It's already starting to get long. I haven't even got to a lot of the problem here. This Murphy's law I'm teaching here tonight, you always have to erase the part of the theorem you need right when you go to use it. Anyway, so now at the critical point 0, 0, we'll test first. D of 0, 0, 0 is, let's see, 6 times 0 is 0, that's fxx. Fyy is 6 times 0 is 0. Minus fxy squared, negative 12 squared is minus 144. What does that tell you? If d is negative, I just erased it. All right. This tells you immediately 0, 0 is a saddle point. If d is negative, then it's going to switch concavity depending on which direction you're moving. Now we try the other point, at the point 4, 4. D of 4, 4, let's see. 6 times 4 is 24, 6 times 4 is 24, so we've got fxx is 24, fyy is 24, and then we subtract off fxy, negative 12 still squared, gives us, let's see, 144 times 4, 5. 576, is that right? I hope. No. Yeah. Yeah, 576, okay. And then minus 144 gives us 432. But it doesn't matter what it is, it's positive, right? Now we can see if maybe there's a relative min or max. So we check it, we check. See also that the second partial with respect to x at that point. What is that? Well, that's, let's see, 3x squared minus 12, I'm sorry, 6x. It's 6 times 4 is 24, is greater than 0. If the second derivative is positive, it means a relative minimum. relative minimum at 4, 4. Alas, I haven't told you what the relative min is. What is it? This is where it occurs. Just like it in calculus 1, it's the dependent variable, right? You said you have a relative, something like this. The relative minimum was at this value of x was the y value. The relative minimum at the point xy is the z value, the function. So it's at 4, 4 of f of 4, 4. You have to go plug it in. Equals, let's see, 4 cubed plus 4 cubed minus 12 times 4 times 4. All right, so 64 plus 64 is 128. Minus 48 times 4, 192. So 64 plus 64 minus 192 is 128. Take away 192 is 64. Minus 61. So it has a relative minimum of minus 64 at the 0.44. And that's it. It's got one relative minimum, one saddle point, and there are no other relative minimum or maximum because critical point is a necessary condition to have a saddle point or a relative extremum. So that's it. Any questions on that one? That's the analogy to relative extrema of calculus 1. And I have to ask you, what did we do for other extreme values in calculus 1? Well, we had global extrema, right? Sometimes called absolute extrema. So we'll make that definition. Now, just like in calculus 1 with a function of 2 variables, I'll be so glad when I get rid of these silly masks. I feel like I talk like the mummy all the time. It's just terrible. Let me know online when you can't tell what I'm saying, please. I sometimes forget that my voice isn't as clear to you as it is to me right here. All right, so now I forgot what everything I was gonna do. If f of x0, y0 is bigger than or equal to f of xy for all xy in the domain of f. I was going to do more on calculus 1 as a background to this, but I got to make sure I can finish the lecture here. I'm going to do Murphy's other law. Always start to build something I can't finish. We may do that anyway. In the domain of f, then what? If it's the biggest value or bigger and equal to every other value, then it must be a global maximum. Also called an absolute maximum. Of f of xy. And I say A, I should call it the global maximum. There is no other if it's the biggest. But there can be more than one point it occurs at. Similarly, if f of x0, y0 is less than or equal to every other value of f of y, for all xy in the et cetera, et cetera. Then the z value, f of x0, y0, is the global minimum or absolute minimum. Of the function. But that's an analogy to calculus 1 also, right? Where in calculus 1, you'd have a curve like this. And what happened in calculus 1 was this, x0 here is a point where there's a global minimum, right, over the whole function values, right? The smallest value it takes on here is f of x0. That's the global minimum of the function of one variable, right? Similarly here, this is a global maximum. F of x1 is the global max. And what do you notice about where these occur? Remember this theorem from calculus 1? If you have, for relative extrema, we want to be on an open interval, so we can take the derivative and go around it. But for global maximum, we're interested in closed intervals because there's a nice theorem for closed intervals. On a closed interval from here to here, A to B or something, A to B, in calculus 1, the global maximum always occurs either at an interior critical point, like the min does here, or at an endpoint, like the max does here. So that was a theorem from calculus 1. If instead of finding a relative minimum on an open interval, you wanted an extrema on the open interval, you wanted a relative extrema, a global extrema on a closed interval, then all you had to do was plug in the function at the critical points and the endpoints, and that was it. Every global extremum occurs either at a critical point or an endpoint. There's a similar theorem for calculus 4 now for functions of two variables. So again, we'll say in analogy to calculus 1, I like that picture, hopefully it motivates this. But with more variables, function of two variables, we have this theorem. Every global extremum, or absolute extremum, of a function of two variables, x, y, on a closed bounded region, that is its domain, R, we'll call it R for region, because it's a plane region, occurs at a critical point of the function or on the boundary of the domain. That's the analogy, and it's a nice one. All right, that's what happened here with a function of one variable. Every global max or min occurred either at the boundary of the interval of definition, right? If this is defined on this interval from A to B, a closed interval means it includes the endpoints, right? And bounded, because technically the whole real line is actually both open and closed. You ever heard that before? I told you calculus is complicated. We haven't gone through the technicalities of definition. So you have to say this is a closed interval, a closed bounded interval of the real number line. Then every global max or min occurs either at an interior critical point or at an endpoint. And I can emphasize here interior, because you can't have it on the boundary anyway, right? The critical points demand that you be defined around the point. Let's say an interior critical point. Well, I guess, no, I'm sorry. All the boundary points would be considered critical points from that point of view. Either an interior critical point or on the boundary of the domain. But this one, just like this is a bounded interval, it doesn't go out to infinity, and it's closed and includes its endpoint. Here, what we mean by a closed bounded region is closed means it includes its boundary. And bounded means it doesn't shoot off to infinity. So it's this kind of a case. Here's the picture. You have some plane region R that doesn't go off to infinity and includes all its boundary points. There's not any point here where it's not defined or something. And then you've got a surface over the top. Like this. And every global maximum or minimum occurs either in an interior critical point like this. Here's an x0, y0. That occurs in an interior critical point where you have a horizontal tangent plane. Here's another one, x1, y1. In this case, the global maximum and the global minimum occur at interior critical points. But it can occur at a boundary, right? If I have a region like this, the global maximum, so here's the domain of definition in the xy plane. The global maximum occurs at this point and has this value, f. So the global maximum is f of x1, y1 at a boundary point. But the global minimum is an interior critical point, x0, y0, and you can't r anymore. Well, you have that similar theorem. All right, and so again, to find global extrema, minima and maxima, you have this test analogy to calculus 1. In calculus 1, what you do is you found all the critical points and plug them all in, and you plug the endpoints in. The largest was the global max, the smallest was the global min. Similarly here, we find all critical points, interior critical points. The boundary points are automatically critical points. Find all interior critical points. To find all possible boundary points. I'm gonna put that in quotes because I haven't said what that means. Theorem only says it occurs on the boundary somewhere. But what you can do is you can make the boundary a curve of one dimension and evaluate it using calculus 1 at the possible points. So find all possible boundary points where you might have a maximum or minimum. And then 3, just plug them in. Because according to that theorem, the largest z value by plugging all these in is the global max. The smallest is the global min, right? Because the theorem actually says more than this. It says that every function, continuous function, put that on here, of continuous f of x, y on a closed bounded region domain one thing is just like maybe you remember from calculus 1, if you had a continuous function on a closed interval, another theorem was that it has a global maximum. And then to find them, you plugged in all the critical points in the bounded endpoints. Similarly here, this will always have a global maximum if it's a continuous function on a closed bounded region. And then you can always find it because the necessary condition is it occurs at either a critical point or a boundary point. And you just have to plug them in and see which one is the largest. That's the global maximum. The largest z value is global maximum. The smallest is the global minimum. Good luck finishing my example. Yeah. Told you these are long problems. I can't finish them either. Well, what can we do with 2 or 3 minutes left, but tell jokes or something, I guess. Didn't bring my sock puppets. I'll start an example. I have to do it next time. Suppose f of x, y, because there's just nothing else to do to put up all those terms, is equal to x, y on the unit disk. X squared plus y squared less than or equal to 1. So it's defined on this closed bounded region that's the unit disk. Find this function's global max and min. Right? So one, what we do is we find the critical point, interior critical points. Then we'll check the boundary points and see where that might have max or min along the boundary. Then we'll just plug all the points in. Critical points are where the two partial derivatives are equal to 0, right? So we need 0 equals the partial with respect to x, which is y. Well, that's the equation. That's the x-axis, y equals 0. But they also need fy equals 0, but fy is x. That's the y-axis, x equals 0. It follows, 3 dots being therefore in mathematics, that 0, 0 is the only critical. That's the only interior critical point I need to check. Now I need to find the boundary points. And then I'll just plug in the candidates from the boundary, plug in 0, 0, and whatever's the largest value will be the max, and whatever is the smallest will be the minimum. To be continued next time. I'll make you all show up just like the TV programs. Really next time. So this is really good though. I mean, this is exactly what you need for all sorts of important applied problems. You want to know how high did the rocket go, or you know what was the highest point on the drumhead when it undulated, this kind of thing, for a surface. So I have to do that next time. I'll go ahead and give you the problems out of this section in case you want to work ahead. However, we haven't done one example with that yet. We just gave the theorem. Here is 13.8, what we're looking at. 9, 11, 15, 31, 33, 35. Oh, good, only 6 problems. But remember what I said? They're all long. So it'll take you maybe 3 class periods. Like took me class period to do 1.5 examples. Maybe this will be 4 class periods. All right, thank you for tuning in tonight. Send me questions if you have them, and we'll finish this example next time. Thank you.